Hello, everyone. My name is Ellis Mimms, and this is my research project, the PMOAB, which stands for the Pine Mountain Observatory and beyond. This is done in collaboration with Pine Mountain Observatory, Fisher Group, and the McNair Scholars Program. Before diving into the Pine Mountain Observatory and beyond project, I first want to give some background on Pine Mountain Observatory, the place where this project was carried out. Pine Mountain Observatory is a research-grade facility owned and operated by the University of Oregon. It is located 34 miles southeast of Bend on top of a mountain at an elevation of 6,300 feet. PMO is under a special use permit from the Deschutes National Forest. While open to the public, so yes, we encourage you to come on our public nights for observations. PMO's primary purpose is research and astronomical observations. Since its opening in 1967, a total of 4 telescopes, including this one you can see here on the right, the Robins, have been installed at the observatory. Pine Mountain Observatory and beyond is a continuation of the project I began 2 years ago titled the Pine Mountain Observatory Deep Field. In this original project, we created our own deep field image by imaging the central region of the Coma Cluster in order to determine how many galaxies we could detect within it and to what magnitude the telescopes at Pine Mountain can see into space. To understand the Pine Mountain Observatory and beyond project, it is important to understand the Pine Mountain Observatory deep field and deep field observations as a whole. Deep field observations are these long-lasting observations of a specific region of the sky, and they're intended to reveal faint objects such as galaxies or stars or clusters. They do this by collecting light from these objects for a certain amount of time. And in order to understand this, it's also important to understand how a telescope works, because telescopes work by bringing in light from objects being observed in order to see them or image them. So this means that for a telescope and for deep field imaging, the more light that we can bring in, the farther or deeper we can see into space, hence the name deep field imaging. And this is why we keep our lenses open for these longer periods of time. Deep field images are very important because they allow us to see into the farthest reaches of space. And being able to look at these galaxies that are far off, we can study distance, age, composition, just a lot of different things. The Pine Mountain Observatory Deep Field was inspired by something, and that something was the Hubble Deep Field. So many of you may have seen this image here, or if you haven't seen that one, you've probably recently seen James Webb had some images come out. Those are examples of deep field images. So the Hubble Telescope, for 10 straight days in 1995, Hubble pointed at a region of the sky within the Ursa Major constellation and gathered all the light it could by holding its lens open. And from that, it was able to detect over 3,000 galaxies, different in size and shape and composition. From the Hubble Deep Field, many things came, such as the Hubble Ultra Deep Field and the Cosmic Assembly Near Infrared Deep Extragalactic Legacy. So it was very, very important. Something important that we need to understand with our deep field is deep field methodology, because not only was this how we created our deep field and how deep fields are created, but we also, to understand the Pine Mountain Observatory and beyond, we need this. So the first step to create our deep field, we first imaged. So we use 60-second exposure times of the Coma Cluster in the INR filter. And we took these observations and we converted them into FITS files, which stands for Flexible Image Transport Systems. So this is how we take these images that this data we get from the telescope and convert it into these files that we can use to analyze and reduce and be able to get a lot of data from them. Next is dark subtraction, and dark subtraction is where we take a calibration or dark file and we subtract that from the original FITS file with the data on it. So we do this in order to remove hot pixels and to create a greater signal to noise ratio. Step 3, which is a very important step, is the correcting for dithering. So during the process of observing, the telescope dithers, which means to move slightly after every shot. And this is done to avoid these hot pixels. So after every shot, the telescope shifts in a random direction. And that means at the very end, all our FITS files of this one target are shifted slightly in these random directions. So to account for this, we have to write scripts to be able to line these up on top of each other, which made step 4 a lot easier, which is stacking, because once everything is lined up perfectly, we can stack these on top of each other and see our final image that we have and be able to analyze it. So here is our deep field, the Pine Mountain Observatory deep field of the central region of the Coma Cluster. As you can see, these red lines and circles are around the galaxies. And the NGC that you see right here stands for New General Catalog of Nebula and Clusters of Stars. So every star, every galaxy, every cluster, every nebula that's discovered, they're put into this catalog. So far within the central region of the Coma Cluster, over 1,000 of these galaxies have been identified. So that is what these are in these boxes and these red circles. These green circles are around Milky Way stars, and the easy way to tell a Milky Way star from these galaxies is you can see these spikes coming off of these Milky Way stars. So this is our deep field. A little bit more into the results. We were able to detect over 354 galaxies. So out of 1,000 galaxies that are known to be in the central region of the Coma Cluster, we were able to detect around 35%, which for a lot smaller of an observatory that we are, and one that's on Earth, so we have to look through the atmosphere, unlike Hubble, who's in space, so they don't have to look through the atmosphere. I think that is pretty good. So that was a little bit about the Pine Mountain Observatory deep field, but now we're going to go beyond that with the Pine Mountain Observatory and beyond. So with this, not only do we want to always keep improving and pushing boundaries at Pine Mountain Observatory, but we wanted to address issues that arose during the creation of Pine Mountain Observatory deep field. So with this project, we aim to create more efficient software intended to analyze and resolve issues surrounding dark frame subtraction that were discovered during the creation of the Pine Mountain Observatory deep field. To understand the main issue that arose during the creation of the deep field, we need to take a look back at the second step of deep field creation, which is dark subtraction. Like I stated earlier, dark subtraction, it's the process of taking the calibration file and subtracting it from the file with the image on it. This allows us to increase the signal to noise ratio. In layman terms, that means to make the stars and the galaxies and other celestial bodies brighter and the background quieter or darker. This also allows us to get rid of what is known as hot pixels. So a hot pixel, I know you guys have heard me mention this like a lot during this presentation. A hot pixel is produced by individual sensors on the camera that's attached to the telescope. It's produced when there's a higher than normal rate of charge leakage, and they usually appear as these maxed out singular pixels. Hot pixels, they can come from not dithering the telescope during observations. But as mentioned earlier, since we did dither the telescope, the hot pixels that we're dealing with during the creation of our deep field, they were already located on the chip and were not a result of not dithering, if that makes sense. While hot pixels may seem innocent, the danger in keeping them in the image is that when we go to try and detect sources, because these pixels have max pixel values, they can sometimes be counted as sources when we in fact know they're not sources. Singular pixels cannot be a source. So these blurry objects here, these are sources, but we know that a singular maxed out pixel cannot be a source. So that is referred to as a hot pixel. So to our dismay, during the creation of the Pine Mountain Observatory deep field, a problem would arise. This problem would come to be known as the hot pixel problem. So when the subtraction of the dark files takes place, hot pixels that are present within the image, they should be removed. During the creation of our deep field, this was not the case. While many hot pixels were removed, some remained, and of those that remained, not all were at the max chip value. As a result, the hot pixel problem, or that's at least what we called it, was born. With Pine Mountain Observatory and beyond, we addressed this problem not just by looking at our dark files, but by improving and creating methods and techniques to help with our data reduction process and file analysis. The hot pixel map. This was our first step in attempting to solve the hot pixel problem. So the goal behind this idea was to create a code that could produce a map of the location of every hot pixel located in a FITS file. So we figured that in order to understand why certain hot pixels weren't being subtracted, we first needed to understand where all hot pixels were located in each of our dark files. The hot pixel map code that I was able to create allows us to visualize where these pixels lie in the array. The hot pixels, so right here where you see the number 65535 in the array, they correspond to their physical location here on the right. And just for reference, 65535 is the max pixel value on our chip. So when we see something reach 65535, we know that that pixel has maxed out. So the hot pixel map was used specifically to pinpoint the location of pixels located at max pixel value. I then generalized this code to be able to map the location of pixels at any specified pixel value in an array. Pixel manipulation. Because the analysis of the physical location of the hot pixels within our darks didn't provide any conclusive reasoning behind why some pixels remain during dark subtraction, our next course of action was to look into pixel manipulation. The pixel manipulation code I wrote allows us to run an image, which is also an array, find all the pixels within that array that are at the specified pixel value, and then change them to the value of the median of the 8 pixels surrounding them. Looking at the array on the left, we see that there are 3 hot pixels. Each of the max value is 65535. So running this code through our pixel manipulation code, which you can see below, we can change these hot pixels to the value of the median of the 8 pixels surrounding them, which can be seen in this array on the right. So as you can see, we have 65535. After taking the median of these 8 by running it through this code, we now have a value 10 that replaces this hot pixel value. The purpose behind pixel manipulation is that in the case where we want to change or remove pixels without affecting the rest of the data within the array, such as in the case with the hot pixel problem, we are able to do so. The reason behind replacing the specified pixel value with the median of the surrounding 8 pixels is that when replacing the pixel, we want to keep the replaced pixel consistent with the data within the array. Also, since hot pixels can lie within the middle of some sources that we may detect, we wouldn't want to replace the hot pixel with a 0 or a random number or max pixel value, as these values may not be representative of what the actual pixel value would be within the source. Instead, this will provide a pixel whose value does not correspond to the pixels around it, which would not be good. Beyond work with our deep field, the pixel manipulation code that I was able to write allows us to clean up our data at PMO without destroying it. While this code can clean up the hot pixel problem that exists, we still wanted to dive deeper into dark files in an attempt to better understand the way we capture our darks and subtract them. So our next step was to go deeper in our dark file comparison. To do this, I created a code for a more extensive fits file comparison. This code allows for us to input a specified pixel value and then run multiple dark files through it, pulling out data from these files, such as the amount of pixels at the specified value, what type of file it is, whether that be a light or dark file, the coordinates of the pixel, exposure time the file was taken at, and the date and time the file was taken at. So unlike the hot pixel map, the dark file compare code or fits file compare code allows us to look at multiple files and their data all at once and in way more detail. So this itself is not the code, this is the output, because the code was it was a lot of code and very extensive. So I figured it would be better representative to put the output of what we actually got. So looking at this and looking at the dark files taken on different nights and years and at different exposure times, we were able to see an increase in hot pixels as the exposure times increased and as years progressed. Now, this was expected, though, as with holding the lens open longer or as the chip continues to age, more hot pixels they'll appear on the chip of the detector. The fits file comparison also allowed us to notice coordinates for certain hot pixels that remain through all nights, years, and exposure times, which does in fact actually support many of the hot pixel mappings of our dark files. So that is a really good sign in that regard. While we weren't able to find the direct cause of the hot pixel problem itself, so why all the pixels weren't being subtracted when we did the dark subtraction, this process did allow us to create better and more efficient methods for data analysis at Pine Mountain Observatory. These methods, including hot pixel map creation, pixel manipulation, and fit file comparison, are a result of this process. The analysis of our dark files did help us also realize that we do need to incorporate additional steps in the Pine Mountain Observatory observing procedure. This includes dark file acquisition at the beginning of every night where observing takes place, rather than only on certain observing runs during the season. This also includes using pixel manipulation to ensure that hot pixels are removed from images before processes such as dither correction or even stacking. With the creation of new code, methods, and techniques, the PMOAB not only represents some of the deepest imagery taken and analysis done at Pine Mountain Observatory, but it will also aid in the future reduction of all astronomical data taken at Pine Mountain Observatory. So that is the project, the Pine Mountain Observatory and beyond. Here are my acknowledgements. A special thank you to Dr. Scott Fisher, Pine Mountain Observatory, the Ronald E. McNair Scholars Program, Dr. Christabel Dragoo, and the University of Oregon Undergraduate Research Symposium. Thank you.